In Chapter 2, we're going to be reviewing concepts such as linear equations, graphing using the Cartesian coordinate system, things like slope, perpendicular parallel lines, all that good stuff. And then we're going to use all that to transition into functions, some basic properties, and as well as focusing on some applications. Next week in our class time, we're going to be focusing on a few real problems where we can use lines to solve them, as well as a little bit more practice with some of the things in algebra. But let's just jump right into it. So reviewing some of the types of linear equations. Linear equations, there's a lot of different ways and forms that you can use. And I wanted to review those three forms for now, and we're going to kind of circle back to them and talk about why they make sense as we progress through lecture. But basically, in Chapter 1 section, when we talked about linear equations in one variable, which is like x plus 5 equal to 11. But basically, what if we have a secondary unknown in an equation x and y? And these are often more common things that we deal with in science, math, and whatever, because a lot of times in the real world, one thing that we don't know is related to something else. Or sometimes one quantity depends on another, which we sometimes refer to as dependent versus independent variables. And that's often the role of x and y within a typical mathematical equation. Now we're going to be focusing on linear equations, which just means there's only arithmetic going on. There's no like squares, division, all that other stuff, because we're starting with the simpler types of equations and we'll work our way into more complex equations as we progress through algebra. But it's a good foothold for dealing with other types of equations and functions as we go. But we often write linear equations in many different forms, such as what we call slope-intercept form, standard form, or general form, depending on your textbook that you're using, or point-slope form, which each one has its use. And actually, there are more forms than just this. But like just to sort of review what these things often look like. And these are things that I'm sure you've encountered in algebra before, but it's worth getting back into them and considering why are we using this and how do we actually use these to do real things. But they could look something like this or like this. And with point slope form, this is going to be what we're going to be focusing on in the next little mini series and when we get back into class. But basically, what I wanted to review is what do these things mean, and when we have it in slope-intercept form, basically the coefficient on x is what we call the slope, often represented by m in an equation, and the b is what's represented within the equation is often what we call the y-intercept. And I want to talk about why are these things true, how do we graph them, and dive really deeply into the why do we call them these things and why does it make sense. And standard form is a way we often see it when we're writing systems of equations. It's sometimes a little bit more useful to write them this way, but in terms of this chapter, it's often how we might encounter them, but it's not so much useful for our purposes. Now we're going to start off with graphing lines. And the same sort of procedure for graphing lines we can use when we're graphing all sorts of different equations and functions. And so this is just sort of a recap on how do we graph, which again, I'm assuming you guys all know how to do, but just kind of talk about some terms and how I do things. But we often refer to it as the Cartesian coordinate system, or you might say a grid, an XY axis, a graph, whatever you want to call it. It's named after one of the first mathematicians to really use it a lot, that's where it gets its name from. But basically, it's a combination of two different axes. And I don't know if you've really thought about this before, but it's like in the last chapter we were talking about number lines, and we can graph a point like 1 or 2 or 3 on the number line, or even shade in intervals on a graph of an inequality. Well, with equations involving both x and y, the issue is we don't have just x as our unknown. We have x and y. So, the solution is to, put an x and y axis on top of each other, and we can use that two-dimensional surface to help visualize the connection between x and y. And that's the whole, reason all sorts of graphs work. And typically the horizontal axis is the x, vertical is the y. That's not necessarily always going to be the case, but that's the general conform in mathematics. And I don't know if you ever wondered why. And also another thing is I don't know if you've thought about, well, why is the right positive and the left negative? It kind of comes from the stereotypical right is good, left is bad, and up is positive in the y direction, and y is negative. Down is negative in the y direction. Again, sort of for the same thing, up is like heaven, down is hell. So you got your positives and your negatives organized in that way, and x is on the horizontal axis and y is on the vertical. But ultimately, it doesn't have to be done that way. It's just conventional. And actually, in a lot of three-dimensional graphing, you add a third axis, which we can't do this on a two-dimensional surface. We can kind of imagine it, something that you do in higher level mathematics a lot more frequently. And actually, sometimes the vertical axis is sometimes the z-axis, and the other axis is called the y. Ultimately, it doesn't really matter what you call what, but so we get the hang of it. Anyways, then in an equation, if what we call a coordinate or a point or an ordered pair basically is representative of x and y at the same time, being a solution to an equation. Because in a linear equation, let's just invent one real quick. Y is equal to x plus 1. The issue is there's not a single answer. Like in linear equations in one variable, we could solve for x and determine, well, what's the answer? But when there's two variables, there is no answer because the equation doesn't describe a certain problem where there is an answer. It describes a relationship, which is sometimes called, some relations are called functions, a very specific type of relationship, which almost all linear equations are functions, but we'll get to that later. But notice that like this point, we would say it's a solution to the equation because if I plug it in, right, x is always the first part, y is the second part. What I would get is 3 for y is equal to 2 plus 1. And since that makes sense, we'd say that that ordered pair is a solution to the equation, and that's why we would graph it. And then we can figure out more solutions because technically there's an infinite number of different points that work in such an equation like this and graph them all together, which form our graph of our equation. And we often call the point in the middle the origin, same term as with a number line, which is where 0, 0 is, where the two axes intersect each other. And then the quadrants are sometimes referred to based on, just the thing you can remember is the doubly positive quadrant to the right and up is quadrant 1, and it goes counterclockwise from there. Just in terms of a numerical convention, which is not really important for our class whatsoever. But anyways, what I wanted to do is do a few practice problems in terms of how do I graph a linear equation. And basically, what you could do is you could just find different solutions, basically find different ordered pairs that work. Often we strategize this by developing what we call a table of values, or commonly called a t-table. So say I wanted to graph the first example from the lecture slides right here. I could always make a graph by hand or print out some graph paper. Graph paper is really nice for doing this too, for those of you who like to be neat and ordered very nicely. But I'm just going to sketch them because I don't have one here, unfortunately. But basically, sorry, I don't want to graph it yet. I want to make a t-table to begin with. But basically, usually we put x and y because that's the order. That's why we call them an ordered pair, because they usually go in order alphabetically, just so we know which is which. But basically, start off with, well, x and y. And my goal is to solve different points that work in the equation. Now, a lot of people say, well, you need to have at least 2 points or 3 points. For lines, really, you only need 2 points to graph a line because it's a straight line. But we wouldn't necessarily know it was straight if we had no idea any of the properties of such an equation. So it's usually better to graph 5 or 10 points if you don't know what it's going to look like. But let's just choose, usually what I would choose are numbers near the origin, which are pretty easy to evaluate, just to make it easier on myself to figure out the behavior of this equation by the point. So I like to often pick values surrounding 0, like from -2 to 2. And if this doesn't really help me, I would expand to more values. And often you might be given a table to fill in or something, and so you wouldn't have to figure it out. But my students have sometimes asked me, how do I know what to pick? Well, you can really pick whatever the heck number you want. And so I usually pick stuff that makes it easy. But let's say we started with 0 here for x. And again, basically I would be plugging it into the equation and solving the other side. You could even start with y and then solve for x, it doesn't even matter. But it's more typical since x we often refer to as the independent variable and y is dependent on x. Again, you could switch which is independent and dependent depending on the scenario. But like this equation is sort of saying that y is equal to this other stuff that if I multiply by 3 and then subtract 4, there we go. So with 0, well, if I plug in 0, 3 times 0 is 0, minus 4 is minus 4. And notice that what that gives me is the point 0 comma minus 4, which you might recall we often refer to this as the y-intercept because it is where the line is going to cross your y-axis. But when we look at the graph, we'll see that more obviously. And also notice that that number, since when x is 0, that whole term makes 0, is quite obviously going to give us the value of y. And, you know, anyways, you can always remember that when x is 0, that's called your y-intercept. And vice versa, when y is 0, that's your x-intercept. Solving some more points, if I were to plug in 1, that would give me 3 times 1 minus 4. 3 minus 4 is negative 1. And then if I plug in 2, I would have 6 minus 4, which is 2. And then with minus 1, I would have negative 3 minus 4 is negative 7. And then negative 2 would give me negative 6 minus 4 is negative 10. And anyways, it's just a matter of picking whatever numbers I want, doing some math, and getting my points. Anyways, if we then plot all of those points or graph them on a graph, which is just, again, just like a number line, but there's two of them, we can try to figure out what this looks like. And since they're linear equations, and that is exactly why they're called linear equations, because their graphs look like lines. And I want, we'll take this opportunity to talk about slope and other stuff like that in just a minute. But I would have 0 minus 4. And remember that x is always on the horizontal axis. So positive means to the right. So like say, for example, 2, 2, that would mean right 2, up 2, which would be, over here, right 2, up 2 would be right about there. And then 1 minus 1 would be right 1, down 1, because again, y direction is up, down. Down 1, and I'll go ahead. I'm doing my best to keep it fairly accurate looking. But again, it's better to do this on graph paper or on pre-graphs because then you don't have to draw it and it doesn't look as ugly. Then 0 minus 4 would be, to the right or left 0, and then up, down 4. 1, 2, 3, 4. And then left 1, down 7 would be down here, and so on. But, once I have enough points to really see, okay, yeah, those do appear in a straight line, we often then connect the dots to finish our line. And I don't know if you've ever really thought about, well, why do I actually connect the dots in these things? Because that's something that, as a student, we often don't think about. We just kind of do what we're taught. But really, it's because this equation is not just a collection of individual points. When I'm solving these points, that's cool and everything. I'm finding valid solutions, but there are many, many other solutions, even in between. Like say, for example, if you were wondering, should I plug in decimals or fractions? Let's say I was to plug in 0.7. That would give me 3 times 0.7, which would be 2.1. Then 2.1 minus 4 would be negative 1.9, and I would get, this other awkward point, 0.7, negative 1.9, assuming I did all that math in my head correctly. But basically, you could get weird other points which are not, right on the grid lines, but that should still be on my line. It's not something that I would want to graph, but notice if I was to go right about 0.7, which would be somewhere about there, and then down 1.9, that would fall along the line, which is really just a pattern outlined by the solid line. Because while I am just graphing points, those points all follow a pattern, and the equation itself is just much more than just a collection of points. It's an entire line. It's sort of like there's a shaded regions where on an inequality we shade in the number line to sort of indicate, well, there's a lot of answers. That's sort of the same thing. We're graphing a solid line to indicate, well, there's a lot of different answers, and those solid line is indicating that. But anyways, the last thing about this is once we have the graph, we can determine things like what's the slope in the intercepts, which we'll focus on more in the next video. But the slope is the general trend of the, basically when we're looking at lines, we can see they go in all sorts of directions with all sorts of steepness. or tilt, or however you want to phrase it. But like with this line, it looks like it's a fairly steep incline, and basically the slope is a way to quantify how steep is that line, and it's always done using the idea of, well, rise over run, or other things like that. But the slope of an equation, when it's written in slope-intercept form, you can actually tell that right by here. And if we kind of look at the steepness, it's often easy to examine the slope by connecting 2 points together with a little triangle like this. And if you connect those 2 points that we found with the triangle, we can see, well, it rose 3 and it ran 1. And if you take the rise divided by the run, that's a way to find the slope as well. And we're going to talk more about this, but I just wanted to sort of show you this and how it pertains back to the equation, and why does it work like that. But if we really think about the math, when we took 3 times a value, this minus 4 doesn't affect the slope, because that's like a static value. It doesn't really matter what x is, we're always going to take away 4. But what is affected for each value is 3. So like if I did 3 times 0, that's 0. 3 times 1 is 3. 3 times 2 is 6. Every time I plug in 1 more, it grows by that many. And if I kind of look at that in the table, as I grew by 1 in the x direction, it rose by 3. And actually, you can actually see the slope in the table of values as well, because for each increase in 1 in x, it grew by 3. And if you just take the ratio of y, which we sometimes refer to as delta y to delta x, that's another way to determine the same thing. But notice that that's a consistent amount. From each value of y, it's growing by 3 for each value of x as it grows by 1. And of course, if you choose weird numbers like this, technically it still fits in the same slope, but it just makes it a little bit more annoying to do those calculations, which is why we typically want to pick those whole numbers. And lastly, notice that the term I mentioned before was the mx plus b, the second part of it, which we refer to as the y-intercept. As I was saying before, notice that happens when x is 0 always, and that's what gives us the y-intercept, which is just where the graph crosses the y-axis, which will always be when x is 0, not just for linear equations, but all equations will always have a y-intercept when x is 0. And that just is always going to be the other number as we see it in this form. So in the next video, we will talk more about intercepts, more about slope, and equations in other forms.